General relativity, step by step. Over the previous few screencasts, we've taken the Einstein field equations, we've linearized them, and then over and over again we've applied various clever techniques to simplify the solutions that we've found. And eventually we've come up with this wonderful, wonderful thing, which is to reduce the metric down to a sum of the flat space metric eta plus something small. And the expression for the small thing is a second rank tensor A times e to the I k alpha x alpha, where the A matrix and the 4 vector k are constant, and it's conventional to write k alpha equals omega 0 0 omega, so we can think about different frequencies for this thing. And we've also discovered that A alpha beta can be written in this form here, if I just write it in a sort of matrix format: T, X, Y and Z, T, X, Y and Z. We've got zeros around here. And the terms that we had were alpha and minus alpha, because you'll remember that the trace was set to 0, and beta. These two numbers are the same because it's symmetric. And alpha and these two terms are the same in size but opposite in sign, because we've insisted that the trace is 0, the traceless condition there. Alpha beta, let me just... I've got a new interface here, so hopefully it'll behave itself a bit better than last time. Equals this. But I'm still not quite used to it, as you can see. I'm not very proficient with it. Right, so what am I going to do? What I'm going to do is I'm going to remind ourselves that the equations are linear. So if we've got a solution f of x, that's a solution, I guess x in general, then that tells me that I can multiply f by any scalar and it's still a solution. It still works. Also, if I've got f of x and g of x is a solution, then that says that f of x plus g of x is also a solution. So we can just multiply by a scalar, and we can add two distinct solutions to get another solution if we find two solutions. And we've kind of got two solutions built into this system here. And of course what I'm going to do is I'm going to consider alpha equals 1, beta equals 0 as one case, and alpha equals 0 and beta equals 1 as another. So let's have a look at that. Let me pinch in a little bit. Or is that pinching out? Okay, so when alpha equals 1 and beta equals 0, what have we got? We've got matrix 0, it's always zeros around here. Quite nice writing these zeros in there. Alpha equals 1 says we've got 1, 1, 0, 0. And of course I can, that matrix there, I can take any combination of that times e to the I k alpha x alpha, any number. For reasons that will become apparent, I'm going to call it an A with a subscript plus. A plus. It's just a scalar, and I'm going to add to that the solution, of course, with alpha equals 0 and beta equals 1. So what did that look like? That's up here, so we've got 1s on the off diagonal there. Oh, that should be a minus 1, of course. That's a plus 1 and that's a minus 1. Plus a, and for reasons that will become apparent soon, I'm going to call that cross. That's another scalar. All I'm doing is forming linear combinations of this one and that one times zeros round here. 2, 3, 4, 1, 2, 3, 4, and we've got zeros there. 1. Seem to have drawn 5. Let's do that. 0, 1, 0. Yes, it's symmetric. Again multiplied by e to the I k alpha x alpha. These are the same in both cases. In fact, I'll make that a little bit more explicit by drawing a line. Actually, I won't. Do that. These two things are the same. Okay, so why have I done that? What are we going to do? Okay, so we've got two components, or two linearly independent components to our solutions here. We've got two scalars here, and of course what I'm going to do is look at them separately and consider them one at a time. But we'll see that they're not horribly different. They're not telling a very different story. Okay, I'm going to stop there. Stop.